Do you remember your days lounging on the marina? Remember how it seemed like the boats had different designs for some reason, even though you were pretty sure they all did the same thing? Boat hull design has been a topic of interest for hundreds of years. The designs of hull configurations is directly dependent on the intended purpose, size, and velocity of the boat. Some common features, such as the low surface roughness on the hull, for example, have remained approximately the same for different vessels. However, the overall design of boat vessels has varied drastically.
This experiment was designed to study the effect of boat hull design on drag. We studied this by observing boat wakes and the vortices produced.
Three key hull designs were examined in this experiment: a flat boat design, a deep V boat design, and a pontoon boat design. These boats were placed in a water channel, with a fish scale being used to measure drag force.
Reynolds number is the ratio of inertial to viscous forces. The coefficient of drag allows quantification of the resistance an object experiences due to the fluid flow. Skin friction is the drag component from viscous forces. Vorticity is twice the angular rate of rotation of a fluid particle, and vortexes are created due to the adverse pressure gradient. Flow visualization in the water channel reveals spatial and temporal details about the flow.
Here we have a flow visualization of our flat boat with a flow speed of 0.32 meters per second. This will be used for comparison with other boats. Our first comparison will be with the deep V boat.
More water is displaced when the deep V is pulled through the water. We can observe from the larger wake that vortices are bigger for the deep V compared with the flat bottom. This also means the drag forces are greater for the deep V hull design.
Next, we will compare our flat bottom hull design with the pontoon.
The wake is seen to be smaller for the pontoon bottom than the flat bottom, meaning larger vortices and greater drag forces with the flat bottom design.
To summarize our results, the pontoon boat experiences the most drag and the biggest vortices when compared with the flat bottom boat and the deep V boat. This is likely because the characteristic length we took was the square root of the wetted area, for which the pontoon has the largest of all three boats. However, our fish scale rig was unable to detect a drag force from the pontoon, introducing error in our measurements. Typical pontoon boats are designed to float on top of water rather than be fully submerged, so they will experience less drag in real use than what has been modeled in our experiment.